Alright, hello everyone. I hope you guys are doing great. So, I'm finally back after a somewhat long break, you can say. Well, the thing was that I was trying to get settled into a new job, a new full-time job, which I currently am. So, yeah, with that, I can say that I will be a bit more regular here. I mean, you can expect a lot of regular videos, weekly videos, I would say. Right, yeah, so with that in mind, I think we can start with today's video. So today we'll be discussing the solutions to Codeforces round 879. So this was a division 2 round and it ended like an hour ago, and we'll be discussing the first 5 problems from A to E. About the problem set, I can say that this was a pretty decent round. Although I had participated after quite a long time, I can still say that the difficulty level of all the problems were quite good. Although one thing that I can't really seem to digest is the number of solves in problem D. I mean, the difficulty was not that much. Like the difficulty increase from C to D was not that much, but even then the number of solves reduced drastically, which I failed to digest. But anyways, we'll be discussing the first 5 problems, and yeah, all the problems were quite good. Problem E especially was quite good, although I think the time limit could have been a little more on the softer side for problem E. But yeah, so yeah, with that in mind, let's start with problem A. Okay, so this is a pretty simple problem. So here we have an array of length n, and only -1 and 1 are present as elements in the array, and we want to make this array good, and the array is good if the following two conditions are satisfied. That is, the product of all the elements is non-negative. The product is equal to 1 and the sum is non-negative. Okay, so we need to tell the minimum number of operations that we need to do to make this array good, and in a single operation, as you might expect, we can flip a -1 to 1 or vice versa. Okay, it is pretty obvious that we will never flip a 1 to -1 because it disrupts both of these conditions, but anyways, so yeah, that's the problem statement. Let's just have a look at the solution. Solution should be pretty simple. So we are at problem A. Alright, so yeah, let's see what's going on here. So the thing is that we need to make the sum greater than equal to 0, which means that we need number of ones to be greater than or equal to the number of -1s. Okay, I think this is pretty obvious because this is the only condition in which the sum will be greater than or equal to 0. And the second thing is that the product is equal to 1, and this happens only when the number of -1s is equal to even, right? Again, something very obvious, and the reason for this is again that if we have an odd number of -1s and we multiply them together, we'll still get a -1, but if we have an even number of -1s, we'll get a 1. Cool, so these are the only two conditions, and with this the problem gets solved pretty easily. So the thing is that first of all, convert all -1s to 1s until sum is greater than or equal to 0. Okay, then check if the number of -1s is even or not. If not, convert one more -1 to 1, right? So yeah, this is pretty simple to think about. So first of all, you definitely need to convert -1s to 1s until and unless the sum becomes greater than or equal to 0. And once you're done with that, you just need to check whether the number of -1s remaining is odd or even. If it is odd, then you will just take one more -1, convert it to 1. The sum still remains positive, but the product becomes 1. Okay, so if there are, let's say, m, so if number of -1s is equal to m, then we will first convert all of these -1s to 1s until the sum becomes positive. So that will be ceiling of m by 2, and then +1 if number of -1s is still odd. Okay, so yeah, this is the answer. So let's just have a look at the code. So first of all, we'll find out the initial sum and the initial number of -1s, and if the initial sum is already positive, then we don't need this m by 2 term that I was talking about, but if it is not, then we do need it. And yeah, so we'll just say that the number of -1s gets decreased by answer, and then we'll just check if the remaining number of minus ones are even or not. So if they are odd, then we'll increment our answer by 1. And yeah, so that's the solution to problem A. Cool. So now let's look at problem B. Right, so the problem statement is quite long, but the thing in this problem statement is that you are given two integers L and R. Basically, you are given two strings L and R, which represent integers of length up till 10 raised to the power 100. And essentially what you need to do is you need to choose two numbers in the range L to R, and you need to choose them in such a way that a function defined on two strings is maximized. And the function is, if you have two strings s1 and s2 of the same length, then you just take the summation of the adjacent elements differences. Okay, so it is pretty clearly defined here in the problem statement. Let's say we have two strings, x equals to this and y equals to this. Then the function that we are interested in is nothing but the summation of absolute values of x1 minus y1 plus x2 minus y2 up till xn minus yn. Okay. Another clarification here is that if the length of the two strings are different, then we'll just pad the shorter string with leading zeros, because that will not change its value in numerical terms, right? Cool. So yeah, we just need to tell the maximum value of that function if we can choose the two numbers independently in the range from L to R, right? Alright, fine. So yeah, let's look at problem B now. We are at problem B. Cool. So here what we can say is that the first thing is, yeah, cool. So the first thing to note here is that if the lengths are not same, if length of L and R are not same, we can simply pad up L with leading zeros. Okay, cool. All right, fine. Now the next thing that we need to look at here is that, let's say we have two numbers L and R. So L is something like this and R is something like this. We know that the lengths of L and R are same because we have already padded them with leading zeros. Cool. So the first case is that if L is equal to R. So what happens if L is equal to R? So if L is equal to R, then we don't really seem to have any choices for both our numbers. So we'll just choose both the numbers equal to L. And so the answer in this case will be 0. Okay, so we can get this case separated from the rest of the analysis. Cool. So now we know that L is not equal to R, and if L is not equal to R, we know that R is greater than L. So there is some position where L and R differ for the first time, right? So let's say this is the position where L and R differ for the first time. And so what this means is that both L and R have the exact same digits in the first few positions, and then this is where they differ for the first time. So let's say L has an X here and R has a Y here. We know that Y is greater than X because we know that R is greater than L. Okay, this is simple basic mathematics. Cool. So now the greedy observation here is that if we need to maximize our differences of adjacent elements, then the first observation here is that in both the numbers that we choose, we need to make, so let's say these are the two numbers that we are choosing. So let's say x1 and x2. So in both x1 and x2, the first three digits have to be z, right? That's pretty obvious because if any digit in the first three digits differ from z, then that number will either become greater than R or it will become less than L, and that is something that we don't want. Okay, now let's look at the rest of the digits and see what we can do here. Cool. So this is the digit that on which the L and R differ for the first time. Okay. So the greedy observation here is that it is possible to make all of these equal to 9. All the differences that we get from here equal to 9, and it is also possible to get the max possible difference from here. And the reason is that first of all, the max possible difference that we can get from here is actually equal to absolute value of x minus 5. And again, the reason here is that we know that both of these numbers have to be in the range from L to R. So let's say that this is the smaller number. So this is the smaller number and this is the bigger number. Okay, so we know that this digit here can't be greater than y, because if this becomes greater than y, then this number will become greater than r, and this digit can't be smaller than x. Okay, so this applies for both of these positions. So we know that the digit here in both the numbers will be in the range from x to y. So the maximum possible difference that we can get in this digit is absolute value of x minus y, and the maximum difference that we can get from all these digits is equal to 9. And it is indeed possible to do that, and the reason is that we can just put zeros here and we can just put 9s here. Okay, so what this does is that this is y and this is x. We know that x is smaller than y, right? Sorry, this should be y and this should be x. Cool. Right, yeah. So then what happens is that this number, if you look at this number, it is strictly smaller than r. So sorry, it is smaller than or equal to r, and it is greater than or equal to l. And if you look at this number, again it is greater than or equal to l, and it is smaller than or equal to r. Reason being that we have all 9s here, and if you look at l, there was an x here, but the maximum number that you can get from the remaining suffix is if you put all 9s here. So this number becomes greater than or equal to l. This number similarly becomes less than or equal to r, and we also know that this number becomes greater than x1 becomes greater than x2 simply because y is greater than x. So all of our conditions are satisfied, and this is greedily giving us the maximum possible value of the required function from all the digits, and so we can say that this will give us the correct answer. So the answer simply becomes 9 times this. So the answer simply becomes 9 times this plus absolute value of x minus y. Okay, so yeah, this completes the solution. I hope it was clear enough. Let's just have a look at the code. Cool, so this is the code. So what you are doing is, if l is equal to r, then the answer will be 0. Otherwise, you are just padding up l with zeros until its size becomes equal to r, and then you iterate from left to right and find the first point of difference. Okay, and the answer will be the difference of the positions, the elements at the position from l and r, and at all the rest positions we can just have 9 in the answer. And yeah, so this is it. I hope the solution was clear. Let's now move to problem C. Cool. Right, so in this problem, essentially we have Alice and Bob playing a game, and what happens in this game is that we have two strings s and t. Okay, and Alice and Bob alternately take turns. So Alice goes first and then goes Bob, and each time they alternate. What happens is that in each turn, Alice will choose either of the two strings. So Alice will choose one of the two strings, either s or t, and Alice will just change one character in one position in that string. Okay, that's what Alice does. Okay, Alice can also choose not to change any characters. That's completely her choice. It is equivalent to saying that it takes a character and then replaces it by itself. Okay, and on Bob's turn, what he'll do is he'll choose one of the two strings, exactly one of the two strings, and he will just reverse one of them. Okay, so he'll choose a string and he will reverse it. Okay, that's what happens. Okay, and yeah, so the goal of Alice is to minimize the number of moves, and the goal of Bob is to maximize the number of moves. Obviously the game ends when both the strings become equal. Okay, so yeah, we need to tell if both the players play optimally, what will be the number of moves that will be played in the game. Okay, that's the problem statement. I hope it is clear. Cool, so let's look at the solution now. So now we are at problem C. Fine. So let's try to analyze this problem, and let's look at the key observation here. Cool, so let's look at the key observation. So one thing that's troubling in this problem is that Alice has the liberty to choose a string from S and T and then change the character. Similarly, Bob has the liberty to choose between S and T and then reverse it. And that is something which is adding some complexity to the problem, right? So what we need to do is we need to remove that complexity. And this key observation will basically help us do that. So the observation is that we only need to look at one of the strings. We don't really need to look at both of the strings. Okay, so we only need to look at one of the strings and not both of them. Cool. Now the reason for this is that in every turn Alice will choose a string and will replace a character. That's fine. That's totally fine. And in each of the moves of Bob, he will choose a string and he will reverse it. Okay. So what will happen is that at any point of time in the state, so if you look at the state of the game, so Alice will take S and she will do some changes and she will get S prime. Similarly, she might have done in her moves some changes to T and we get T prime. And so this happens when we only consider the moves of Alice, but if we also consider all the moves applied by Bob, then what happens is that Bob might have chosen S and reversed it an odd number of times. So then we'll had reverse of S prime. Okay. And Bob might have chosen T and he might have reversed it an odd number of times. So we'll get reversed of T prime. Okay. So the state will be one of the four, either S or S prime, and either T or T prime. Okay. This is going to be the state of the game at any point of time. So we don't really need to look at both the strings separately. We just need to look at one of the strings. So let's say S is equal to something like this and T is equal to something like this. So what we'll see is we'll just try to make S equal to T. As Alice, we'll try to make S equal to T. So we'll just have a look at all the characters of S and we'll try to make all the characters of S equal to all the characters of T. Okay. And we'll forget about making changes on T itself. Okay, we'll just make changes on S and that will do our job, only because at each point of time S will be either in its initial form or in its reversed form, and the same goes for T. Okay, cool. And the main observation again here is that we can make S equal to T or S equal to reverse of T. It doesn't really matter, because if we make S equal to reverse of T, in the next move Bob will have to choose either S or T, and no matter what he chooses, both the strings will become equal in the next move itself. Okay, cool. So if we make S equal to T, we are done. If we make S equals to reverse of T, we need exactly one more move. Right. So with these observations, we can simply come up with with the solution to this problem. So the solution is pretty simple. So let's say that S and T differ at M positions. So let's say S and T differ at M positions. Okay. So what we'll do is Alice will try to make S equal to T or S equal to T prime. So it also makes sense to look at the number of positions in which S and reverse of T differ. Not T prime, this should be reverse of T. So let's call this M1, and S and T prime differ at M2 positions. M2 position. So now this problem is just reduced to a simple case analysis. Okay, so let's say that case 1. So case 1 is M1 is even. Okay, so what happens when M1 is equal to even? In fact, case 1 is Alice tries to make S equal to T. Alice has two choices. Either she will try to make S equal to T, or she'll try to make S equal to T prime, S equals to reverse of T, and in the next move Bob will just reverse either S or T, and then both of them will become equal. Okay, cool. So this is case 1. So here we have again we have two cases. So case 1 is M1 is even. obviously in each move, if Alice is trying to make s equal to t, she will just pick each character which differs in s and t, and she will just try to make them equal. Okay, so it will take Alice m1 moves, right? So it will take Alice m1 moves, and so when Alice has made m1 moves, Bob will have made m1 minus 1 moves, obviously because Alice moves first. So Bob will have made m1 minus 1, which is odd moves. Okay, so now if Bob has made an odd number of moves, then it is pretty obvious that at least one of them will be reversed, right? So at least one of them will be reversed. So what that means is that even if Alice has converted all of the even if Alice has corrected all the m1 positions, we need another move by Bob to make s equal to t, right? And this is what happens in this case. Similarly, so total number of moves that we need is 2 times m1 here, right? Similarly, if m1 is even, the total number of moves, m1 is odd, the total number of moves will be 2 times m1 minus 1, because we won't need another move by Bob here. And similar is the case analysis when m2 is even and when m2 is odd. Okay, so we can do exactly the same thing and make cases. So I guess the solution is pretty clear by now. So let's just have a look at the code, which will give you guys more clarity, right? All right, let's see what happens here. Cool. So we take in s1 and s2. So if both of them are equal, we simply return 0. Okay. Otherwise, this is the first case where we try to make s1 equal to s2. Okay. So if we try to make s1 equal to s2, first of all, we try to find out m1. Okay. Now, if m1 is odd, we'll need 2 into m1 minus 1 operations. Otherwise, we'll just need 2 into m1 operations. This is because of the case that I had just explained. So this is the case that I just explained. So m1 is even, and one move of Bob is still left here. To make s equal to t, right? Cool. So yeah, this is why we need 2 into m1 moves, and here we can just say m1 is odd. So we already have s equal to t. So we don't really need another move by Bob. And similar is the case analysis here, right? So yeah, this is the solution to problem C. I hope it was clear enough. Cool. Now let's move to problem D. Problem D now had very less solves compared to what it ideally should have had. So I think the solution should be quick here. So let's see what this problem states. So this problem goes like this. So we have a class with n students and there are m topics to learn. Okay, and the ith student has learned topics from Li to Ri, right? And what happens now is that the teacher takes a quiz, and in the quiz he can ask one topic no more than once. So that's what will happen in a quiz. And for each topic, if a student knows the topic, its counter will be incremented by 1, and if he doesn't know the topic, then his or her counter will be decremented by 1. Okay, so that's what happens. And what we need to do is, after the quiz has been ended, what we need to find the maximum difference between the counters of any two students that is possible. Okay, so yeah, I think the problem statement might have been a bit confusing here. That's why the number of solves were less, but you never know. So let's start with the solution. So we have problem D here. So essentially here we are given with a set of intervals. Okay, we are given with a set of intervals from Li to Ri. So let's say that we sort the intervals by their left coordinate. Okay, and this is the list of intervals that we have, something like this. Okay, these are all the intervals that we have. Okay, so now let's focus on every interval. Okay, so let's focus on this particular interval. Okay, let's say that we are fixing which interval we will make the maximum. Okay, so this is the main idea here. we fix the interval, or maybe we fix the student which will have the maximum marks, and then we try to minimize the student with minimum marks. Okay, so yeah, that's the key idea here. So we'll just fix the interval which we'll fix the student which gets the maximum marks, and then accordingly we'll try to find what can be the minimum possible value of the student which gets the minimum marks. Okay, so let's say that we have fixed this particular interval as the student which gets the maximum marks. Okay, so now the thing that matters the most in this problem is that any interval any number that we pick and that number occurs in both the intervals and it doesn't occur in both the intervals is useless. Okay, so if a number occurs in both max interval and min interval, or it doesn't occur in both of them, is useless in the quiz. And the reason for this is simply because if it occurs in both of them, then both of their marks will increase by 1, and if it doesn't occur in both of them, then both of their marks will decrease by 1, and the difference will still remain constant. Okay, so this is a simple observation here. So we are only interested in the intervals. So numbers which occur in the max interval, the max students interval, let's call it that, and not occur and don't occur in the min students interval are what we are interested in. So the reason is that these are the intervals which will increment the counter or the marks of the student by 1, which is intended to be the maximum student, and it will decrement the marks of the student which is intended to be the minimum student by 1. Okay, cool. So yeah, this is our job. Our job is to maximize such numbers in the quiz. Okay, that's our job, and this is all that we need to do. So obviously one thing that we can do is we can ask all numbers which are in the range of the fixed maximum. So we'll just iterate on the maximum. Let's say we have fixed the maximum to be I. So let's say this is I, this is the ith interval. So let's say we have fixed that this is going to be the maximum. So all numbers in L of I to R of I, there is literally no problem in asking these numbers. So we will just ask them one by one, and this will increment the counter of the maximum student to Ri minus Li plus 1. Okay, cool. Now all we need to do is we need to maximize the number of numbers which don't occur in another interval, because that is when that interval's value will decrease, and that is when we'll get a benefit of 2 in our answer, right? Cool. So what we can do then is we can just we can just choose which interval is the best suited to be the minimum interval, and let's see what comes here. So if we have an interval which doesn't intersect with our maximum, then it is ideal to choose that as the minimum interval, because we can just end up asking all the problems here and we'll not ask any other problem. So this student's counter will always decrease, right? And our counter will always increase. So the answer will be 2 times Ri minus Li plus 1. Okay. So one thing is, this is case 1. Let's formally write it down. Case 1, if there is a non-intersecting interval with the interval of the ith student, then answer is 2 times size of interval I, which is Ri minus Li plus 1. Okay. Now this is pretty obvious because in every move that we play, we will simply have a +1 in our counter and a -1 in the counter of that particular interval which doesn't intersect with us. Okay. Otherwise, again, this is pretty simple. The case 2 is when all the intervals that are there, they intersect with us. We just need the interval whose intersection with us is the smallest. Then we'll just remove that much part. We'll just remove the part that intersects with us, and we'll just double the rest of the part, and that will be our answer. And now so now let's look at it in a different way. So this is the interval that we are interested in. Okay. And all the intervals which are present, they intersect with us. Something like this. Okay. So this is our main interval, this one. And what we need is we need to find the length of the shortest intersection. Okay. In this case, we can see that this is the length that we are interested in. So there are basically just 3 cases to consider here. So case 1 is that the interval completely lies within us. So this case is intervals like this, right? These intervals, they lie completely within us. So this is case 1. And then we have case 2, which is the interval is to the left of us. Interval begins to the left. And case 3, it begins to the right. Okay, cool. So we are just interested in the leftmost point of the interval. So case 2 says that the interval which we are keeping as the minimum, that begins to the left of our interval, and the other case is that the interval that we are keeping as the minimum, that begins to the right of us. So all these cases can be very easily analyzed, and we can just keep a few arrays. So what we can keep is, we can keep the smallest in the prefix array. Similarly, we can keep smallest in the suffix array. Okay. And so this basically will denote the index of the interval whose size is smallest in the prefix. Okay. And same goes for this array. So using these 2 arrays, we can essentially find out the answer to case 1. And now let's talk about case 2. So case 2 says that the interval begins to the left of us. So it is very easy to see that if the interval is beginning to our left now, then it has to end. So its Ri should be small. Ri should be smallest. Right, here you can see in this example that this is the interval that we are interested in, and its Ri is smallest. Obviously, if it is starting to our left and it is intersecting with us and we want the intersection to be as small as possible, then it should end as early as possible, right? So what we'll need is, we'll need smallest r in the prefix array. And similarly, we can analyze case 3, which is that the interval begins to our right. So if it is beginning to our right, then we need an interval which starts as early as possible. In this case, we are interested in this particular interval because it starts as early as possible, and so its intersection will be as small as possible. So we need smallest L in the suffix. So we can just use simple dynamic programming, or just how we calculate prefix sums, stuff like that. So using that, we can maintain all of these 4 arrays, and using these 4 arrays, we can handle all of these 3 cases, right? Cool. So that's the solution to problem D. That's why I was saying that it's not that hard, and the number of solves don't really justify it. So yeah, let's have a quick look at the code. So the code is somewhere here. So this is a function intersect, which returns the size of intersection of 2 intervals. Okay, cool. So what we do is, we first sort all the intervals by their left endpoint, and then we build all these 4 arrays. It's pretty easy to build them, right? So this is the minimum r in the prefix, and this is the smallest in prefix. Then we have maximum L in the suffix, and we have the smallest suffix. Okay. Maybe somewhere I said that we need the smallest L. Yeah, so this should be the largest L. I hope that was clear. Obviously, as you can see here, we are picking this particular interval and it has the largest possible L. Okay, cool. So all of these arrays can be built pretty easily, and then we just handle both the cases separately on the left side and on the right side. Okay, so yeah, that does our job. We just use this intersect function to make our lives easier. Fine, so yeah, that completes the solution to problem D. I hope it was clear enough. Also, if anything is unclear in whatever I am explaining right now, you are free to write down your queries in the comments and I will be happy to help you. Okay. So with that in mind, let's now start with problem E. So problem E was also a pretty interesting problem, although in the contest I kept getting TLE, even though my solution was n log square n, and the current solution which has been accepted is still n log square n. But anyways, let's see the problem. So the problem is that you have an array of length n. What you do is you write down the LCMs of all the subarrays of this array, and you get another array B, and essentially you need to find the MEX of that array B. So you need to find the smallest integer which is not the LCM of any subarray of the array. Okay, so that's the small problem statement that we have. Cool, I hope the statement is clear. Let's now start with the solution. So we are at problem E. Cool. So let's start the solution with the key observation here, and maybe we'll also use a fact. So a fact which is pretty common in competitive programming and in number theory in general is that for a number n, the number of prime numbers in the range from 1 to n is around n over log n. Okay, so number of primes smaller than n is big O of n by log n. Cool. So this is a fact that we are going to use here. Okay, so what we can say is that if we take n log n numbers, then we'll get around n primes. That's the fact that's just a translation of this fact. If you replace n over n by n log n, then you get the second statement. Fine. Right. So what we can say is that in the first n log n numbers, so let's say we have n log n and we multiply it by, let's say, 10. So in the first 10 into n log n numbers, we will let's say we don't multiply it by 10, we add some number. Let's say we add 10 raised to the power 6 here. In these many numbers, okay, in these many numbers, we will have strictly more than n primes, right? So this is something that is a fact, and it is generally known to people who've been into competitive programming for long enough to reach problem E in a contest. Anyways, even if you are trying to upsolve problem E, then I expect you to know such a fact already. Okay, so we know that if we say that, let's say this number is called limit. So if we choose limit is equal to this, then we will get strictly more than n prime numbers. And if we are getting strictly more than n prime numbers, then we can be sure that MEX of all LCMs will not exceed limit. Now why is this the case? Why will MEX of the LCMs not exceed this limit? That is because, let's say we have n plus 5 prime numbers. Okay, so we have n plus 5 prime numbers, and what happens is, let's say we have n plus 5 prime numbers less than equal to limit. Okay, now what that will do is that that will ensure that we cannot have all of them in the array. And we also know that MEX of a subarray is a prime number only when all numbers in the subarray, so it's a prime number P only when all the numbers in the subarray are equal to p or 1, right? So we need at least one p, right? So the fact is that we need at least one p to make MEX, so sorry, to make LCM is equal to p. Now this is again a very mathematical and basic mathematical fact that if the LCM of a sequence is equal to a prime number, then we will need at least one prime number, right? So the sequence will contain some p's and it will contain some ones. It can't contain anything else, because if it will contain anything else, then the LCM will be disrupted. It won't remain p, right? So if we have more than n prime numbers, then the LCM cannot exceed that, right? The LCM can never become that particular prime number. Okay, cool. Because we have just n numbers in our sequence, even if we have the first n prime numbers, the n plus 1th prime number can never be there in our sequence. Okay, cool. So I hope this is clear. So we have n plus 5 prime numbers. This is just some random number that I have taken. So if we have n plus 5 prime numbers less than equal to limit, then even if we have the first n prime numbers in our sequence, we won't be able to have the n plus 1th prime number, because we only have n numbers in the sequence. Okay, so we can take this as our limit, and we can say that the LCM, the MEX of the LCMs of the subarrays will never exceed this number. And just to be safe, we can take limit is equals to 10 raised to the power 8, something like that. Okay, so if you take limit equals to 10 raised to the power 8, it is sufficiently larger than n log n to make sure that the number of prime numbers in the range from 1 to limit is strictly greater than n, and so the answer is strictly smaller than limit. Okay, cool. So that makes our life very easy, because now we are only interested in the GCDs which are less than or equal to limit. Okay, we are only interested in not GCDs, sorry, LCMs which are less than or equal to limit. Rest can be ignored. Cool. We have proved that the answer will be less than or equal to limit, so we are only interested in LCMs which are indeed less than or equal to limit, and the rest can be conveniently ignored. Cool. So now let's look at another thing. So let's look at all the LCMs ending at index I. That means the LCMs of all the subarrays that end at index I. Okay. So the fact that the claim that I'm trying to make here is that the number of distinct LCMs which are less than or equal to limit will be very small. And by very small, I mean around 40 at max. Okay, 30 to 40. Now why is this true? So this is true because if we have an LCM and that LCM in a subarray changes, the LCM can only change if it is being multiplied by some number. Okay, so LCM only changes when it is multiplied by some number, right? If you look at a sequence of all the LCMs, so this is the index I that we are interested in. Sorry, yeah. So if you are interested in all the LCMs which end here, then these are all the subarrays that you have. And you know that the LCM is an increasing function. So LCM is an increasing function, and it only increases when it is multiplied by some number, right? So if LCM increases, then it is multiplied by at least 2. Okay, if LCM increases, it is multiplied by at least 2. Okay, so it cannot increase more than log of limit times, and even 30-40 is a large number. We can safely assume this to be around 25. Okay, so we can say that we are only interested in around 25 numbers which end at a particular index. So now this problem has been conveniently solved by us. So what we can do is we can just maintain a set of all the LCMs that end at a particular index. So we maintain let's say LCMs of I, all distinct LCMs which are less than or equal to limit and end at index I. Okay, so now we can transition from LCM of I to LCM of I plus 1 pretty easily. So this can be done by iterating on all elements in LCM of I and taking their LCM with A of I plus 1. Okay, and we'll just check if this new LCM that we have got, it is smaller than or equal to the limit or not, and we're done, right? So we'll just iterate on this set every time, LCM of I, and using LCM of I we can find out LCM of I plus 1, and we can make sure by the claim above that the size of these sets will never increase 20, 25, 30, and this way we can keep track of all the elements which are occurring as LCMs, and then finally we can just iterate from 1 to infinity and just check the first number which doesn't occur, and we can be sure that we will find this number very quickly because I've already proved that the answer will be in the range from 1 to n log n, right? So yeah, that's it, that's the solution. Let's just have a look at the code. So the code is pretty simple. What you'll do is you'll set the limit to 10 raised power 8, and then you'll have a set as ending. So initially the set ending is empty, and what you'll do is you'll create a new set called new ending, which denotes the set of all the relevant LCMs ending at the ith index. So you'll insert AI in it if AI is less than limit, and also you maintain another set all LCMs, which basically denote all the LCMs which can be there as an LCM of a subarray, right? We know that the number of elements in this set will also not exceed 20n or 25n, something like that. So we'll just iterate on the previous ending set. We'll take the new LCM. We'll check if it is less than limit or not. If that's the case, we'll insert it in our new set, and we'll insert it in our global set as well. And then we'll just swap ending with new ending. Okay, and that will do our job. So now in this particular set, all LCM, we will have all the LCMs which can be present as an LCM of a subarray. And finally we can just iterate from 1 to infinity and find the first element which is not present in the all LCM set. So yeah, that will do your job, and that solves the problem. During the contest I was trying out a different approach using sparse table. That was still n log square n, but somehow it was giving me a TLE. But anyways, this is a much more cleaner approach and it works as well. So I hope this is clear. If you guys have any doubts, you are free to write that in the comments. I'll be happy to help you. With that, we've come to the end of this video. Thank you for watching, and I'll see you in the next one.